Hello again and welcome back to another instructional video. Today we're going to look at solutions. If you remember in the last video we looked at gases, gas variables, and how temperature, pressure, volume, and number of particles are all related when it comes to a gas. Today we're looking at solutions, and specifically probably we're looking mostly at aqueous solutions, meaning solutions that are formed by taking something and dissolving it in water. Is there a limit to the amount of solute that will dissolve in a solvent? That might be a potential question that you might want to look at. Let's first of all just make sure that we understand some of our terminology here. When we talk about a solute or a solvent, solute is the substance being dissolved. So it might be like a solid, like let's just say table salt, NaCl or something, being dissolved in the solvent. The solvent would be the liquid in most cases. It doesn't have to be, but in many cases you think of a liquid as being your solvent. This is doing the dissolving. Okay? In many cases, the solvent is in greater quantity than the solute, so that might also just help you figure out which is which. So in my example of NaCl, if you took sodium chloride and you dissolve it in water, obviously water is the solvent, NaCl is the solute. So solutions are very useful. We use them every day, and there are solutions that are very useful. You drink solutions, you apply solutions to your skin, you use solutions for many, many different reasons, and we're going to talk specifically about whether a solution is saturated or unsaturated and what that means as we look at these models. Alright, in model 1 we do have saturated and unsaturated solutions. Beaker A and B, we are told, are both unsaturated, and we're just going to make some observations. We're just going to use our scientific skills and make some observations with beaker A and beaker B. Notice here it says that all beakers contain 10 grams of water. Same amount of water, that's your solute. All beakers are at the same temperature. All solutions are stirred for 2 hours. And the solute is the same substance in all beakers, so you've dissolved the same thing in there. The only difference is you've got 1 gram of the solute in beaker A, 2 grams of the solute in beaker B. Okay? Those particles right there, those dots are representing the relative quantity of solute that is in there. So you've got 5 here, obviously we have 10. It's probably going to ask to do this in a little bit. Dissolve number of solid particles, we don't see any solid particles. If they are kind of floating in the substance, that would be a dissolved particle. So dissolved particles are going to be shown as they're kind of floating in the substance, in the solute, or solvent, sorry. Solid particles, you would see those at the bottom of the container, which there are none in beaker A and beaker B. These are saturated. Saturated here, we have C, D, and E, we are told they're saturated. Now this, the D and E, it's pretty obvious that they're saturated, meaning that you've got solid particles down here that no longer can be dissolved in our solute, or sorry, our solvent. And down here we've got solid particles that are kind of at the bottom of the container, and our solvent is not able to dissolve those. So this is saturated, meaning it is holding the maximum amount of dissolved particles that it can in the solution. And these down here at the bottom, they're out of luck. They are not going to be included in the solution and cannot be dissolved. Just too many of them. Beaker C, you notice we are told that it's saturated, but there are no solid particles down here at the bottom. That must mean that it's right at the maximum amount. If you were to add one more particle, one more little bit into beaker C, it probably would not dissolve because it is maxed out. Okay? It's maxed out. One more particle, you then would see something at the bottom, but we are told that it is saturated. We just don't see that it's obvious because there's nothing at the bottom there. Okay? Alright. Which illustration below represents a solute particle in solid state in water? So this here, this is showing you that you've got particles that are solids. Here, these are in aqueous solution, AQ. So this is situation B, situation A. What variables are controlled in all 5 beakers? I kind of mentioned this already. You've got same amount of water, same temperature, same stirring amount, same type of solute. Okay, all of those are fixed, controlled. Count the particles present in each beaker. Fill in the table to show the number of dissolved and the number of solid, and we did that already. 5 dissolved, 10 dissolved, 0 solid, 0 solid. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 maybe, 18, 0. Here we should have 18 again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, and we're going to have 18 there. But now in D and E, as I already mentioned, you're going to have some at the bottom that were not able to be dissolved. So we've got 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, they had 17, sorry. And I don't know how many, I'll count them. 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I don't know, around 27 or so. Okay, I might have miscounted there. All right. Count the particles present in each beaker. We did that. And which beaker represents unsaturated? So that is A and B. There's still more room for more particles to be dissolved in A and B. Saturated are C, D, and E. They are maxed out. Okay, no more room for any more dissolved particles in C, D, and E. Beakers A through E in Model 1 are depicted as representing 5 different or separate solutions. They could also be considered as 5 snapshots of the same beaker over time. In other words, if additional measured quantities of solute were stirred into beaker A at small increments over time, then beakers B through E would result. So what they're saying here is, let's say you start with beaker A, and then you start to pour more of your solid into beaker A, you might end up with beaker B. And then you keep pouring more in, and you might have beaker C. And then you keep pouring more into the same beaker, and then you have D, and then E as you keep pouring more and more of whatever the solute is, whatever the solid is that you're pouring in there, you might see the result as you pour more and more in there. Okay? When a small amount of additional solute is added to an unsaturated solution, what happens to the number of dissolved particles? Provide specific evidence from Model 1 to support your answer. So a small amount of solute is added to unsaturated. What happens to the number of dissolved particles? Well, the number of dissolved particles is going to increase you're going to be able to retain more and more particles dissolved in the solution as you add more and more. Okay? So you're going to see more and more here. From A to B to C, you see an increase, 5, 10, and then 18. When a small amount of additional solute is added to a saturated solution, what happens to the number of dissolved particles? That's never going to change. That will not change. Once it's saturated, once you reach beaker C here and it's saturated, the number of dissolved particles is never going to go past 18. Okay? When a small amount of additional solute is added to, oops, sorry, it doesn't change, no change. All right? Predict what would happen if a small amount of additional solute was stirred into beaker E in Model 1. If you have additional solute, meaning like your salts, your NaCl, if I try to put more in here into beaker E, and I add more and more of this solute, whatever that is, I'm going to end up seeing more and more solid form at the bottom of your container. we're going to have more and more crystals down here. This pile is going to get larger, okay, as a result. More solid at bottom. The solid that kind of settles out of a solution, that is called a precipitate, by the way. Precipitate. Okay, saturated. What does it mean? Well, I've kind of already said you have reached the maximum amount. Saturated simply means that you have reached a point where you can no longer dissolve any more of a solute, or that particular solute, in that solvent. You've reached a maximum. All right, beakers D and E are labeled as saturated. Well, that's because they have solid at the bottom. You can see it. Okay, solute and solvent, we can use those words in our definition. So basically, in order to write a sentence here that explains why D and E are showing something that's saturated, you could simply say that the solute, you see solute crystals. You see crystals of the solute at the bottom of the container, and the solvent is unable to dissolve all of the solute. And that is evident because you see solid at the bottom. You see crystals at the bottom of your container. What feature in the beakers in Model 1 would typically enable a student to distinguish a saturated solution from an unsaturated, saturated one simply by looking at it? Again, you have the solid particles at the bottom of your container. Okay? Beaker C in Model 1 is shown as saturated. Oh, C. Let's look back at C. Remember C? C was a little bit different. You did not see the same solid crystals at the bottom of the container, but yet we are told it's saturated. So, how are we going to know that beaker C is saturated? Just by looking at it. Just by looking at it, you're not going to be able to tell, because you don't see these dissolved particles. You can't see them. We're drawing them, but you can't see them. You don't see them. This beaker C, beaker A, and beaker B are all going to look very, very much alike. You will not be able to distinguish one from the other. What you can tell is if it's saturated or unsaturated by adding more. You take a small amount of solid and you put it in there, and you stir it up, and if it's able to stay dissolved, then it was unsaturated. Okay, you add some, and if it still is not having any solid at the bottom of the container, unsaturated. But if you add even a minute amount of solid and you put it in there, like in beaker C, you would see solid forming at the bottom of this container because it is saturated. It can't hold any more. If you introduce some more, it's saying, nope, sorry, can't do it. It's going to have to stay as a solid, and it'll go to the bottom of my container. Okay? And that's what 9 and 10 are talking about here. If it's just a clear solution, you won't be able to tell. So what you do is you add more and see what happens. Add more solid. Add more solid and see what happens. If it stays dissolved, that additional solid that you just put in there, then it wasn't saturated. If it doesn't dissolve, then it was saturated. Solute dissolved versus solute added. All right, here we took an experiment, and we collected some data. We have an experiment in which a measured mass of solid is added to 10 grams of 20 degrees Celsius water. The mixture is stirred and allowed to sit for 3 hours. 10 separate trials are conducted for the experiment. So we did 10 trials. It's always a good idea to do a lot of trials because then you're averaging things out. Maybe one is too high, too low, whatever, and you have the average as a result here. But in this case, the reason we're doing 10 trials is because we're going to change the mass of the solute. That's going to increase, and we're going to see the mass of the solute that did dissolve. We're going to see the relationship, what happens here. Okay? So the mixture is stirred and allowed to sit for 3 hours, 10 separate trials, and we're adding a solid to 10 grams of water. This is not going to change. 10 grams, not changing. What is changing is the mass of the solute that is adding. We add 1, then we add 2, 3, 4, etc. And we're looking at the mass of the solute dissolved. How much stays dissolved? Okay, 4 of the trials in Model 2 correspond to beakers A, B, D, and E from Model 1. Write the letters of those beakers next to the corresponding trial numbers. Well, let's look and kind of compare these numbers to the numbers back up for each of the models. So, you have here 5 particles dissolved, then 10 particles dissolved. After you put in a gram, 2 grams, 3.6 grams. Okay, so here is your mass of solute that is added. 1, 2, 3.6, 7, and 9. So 1, 2, 3.6, 7, and 9. Those are the amounts for your model up there. Let's see if we can find them down here. 1, 2, we didn't add exactly a 3.6, then I think it was 7 and 9. Okay? There's your A, B, D, and E. Identify the following variables in the experiment. So our dependent variable is, right here, the amount that we're adding, mass of the solute added. Independent variable is going to be mass that is dissolved. Control. What's control? All of these are put into 10 grams of water and temperature. So we have 10 grams of water. The temperature is controlled, as well as, I believe it said here, stirred and allowed to sit for 3 hours, so that would be controlled as well. Sketch a graph of the data for the experiment in Model 2. A space has been provided next to the data table. Be sure to consider which variable belongs on each axis. The reason why they say that is because we're going to put the dependent variable on the x-axis, the horizontal axis, and the independent variable is going to be your y-axis, your vertical axis. So I'm going to just sketch something. Mine's going to be really crude, kind of a rough sketch, but we have here 1 through 10. Grams added. And then along here, so I would label this axis down here, this would be mass added, and I would put grams in parentheses to show my units. Over here I have mass dissolved, and again I would put grams. So I'm just going to pair these up. When I put in 1, well, I'm going to expand this a little bit here, spread this out. I'm going to count here. This is going to be 1, 2, 3, and 4. Okay, so when I added 1, 1 was dissolved. I'm going to put a point right there. When I added 2, 2 was dissolved. I'll put a point right there. When I added 3, 3 was dissolved. Right there. When I added 4, I only have 3.6. So here's 3.5, 3.6 is right around there. So 4 and 3.6. Notice now, for all of the rest of them, no more is going to be dissolved. So basically what's going to happen is this is going to flatline. So 5, 3.6, 6, 3.6, 7, 3.6, 8, 3.6, 9, 3.6, and 10, 3.6. Your graph basically is going to look like, okay, if I had a nice straight edge, it would look like that. So you can see what happens is you add more and more of the solute and it all is going to get dissolved until it reaches a point where, nope, this is my saturation level right there. Once you reach that saturation level, it doesn't matter how much you add, you will never have any more beyond this point, beyond this 3.6 here. You'll have no more beyond 3.6 ever dissolved. Okay? So which trials represent solutions that are unsaturated? Those would be trials 1 through unsaturated 1, 2, and 3. As soon as you get to 4, you've got it maxed out right there. Okay? Actually, it was maxed out as soon as you add 3.6, and we did that in beaker C up here. Beaker C had exactly 3.6 added, and it's saturated. In our experiment, we didn't add exactly 3.6. We added 3, and then we added 4. Okay? So 1, 2, and 3, unsaturated. All of these would be unsaturated. And then as soon as you get past that, all of these down here, 4 to 10, saturated. Describe the feature in the graph that can help you identify the saturated solutions. Well, the saturated solutions are going to happen once the graph flattens out. Once the graph goes flat, you know that you have saturated solutions. Okay? Which trials in the experiment in Model 2 would have visible amounts of solid in the bottom of the beaker? Well, that would be 4 through 10. Remember, right at 3.6, you won't have anything at the bottom, but it's still saturated. If you write perfectly at 3.6, if you've added exactly 3.6. But here, 4 through 10, you're going to have something at the bottom of the beaker because you've added too much. Okay? So that would be trials 4 through 10. In trial 8, determine the mass of solid remaining at the bottom of the beaker. So basically you're saying here, well, if I added 8, only 3.6 has dissolved, then I've got left over at the bottom here the difference between those. And you can do that. Imagine that the contents of the beaker for trial 8 are vigorously stirred and then poured into filter paper in a funnel. Basically what they're saying here is if you have a funnel and then you put filter paper in there, that paper is going to collect any solid. But the solution and the dissolved particles are going to pass through. So if you take this right here, trial 8, remember we've got the difference of these two numbers is going to give us, that's 4.4, right? You have 4.4 grams of solid that did not dissolve. If you take this solution and you pour it through our filter paper, the solution is going to drip through. The liquid that drips from the filter, that's called the filtrate, is it saturated or unsaturated? You're going to have, the solution is going to pour through and you're going to have collected down here in some beaker, you're going to have a saturated solution. And all of the 4.4 here is left behind in your filter paper. But the 3.6 in the solution, that's dissolved. That sneaks through, and you've got a solution down there that's got 3.6 grams dissolved. That is saturated. Remember, it's saturated right up to 3.6 and beyond, or at 3.6 and beyond. Okay? Which beaker in Model 1 best represents the filtrate that would be obtained? Well, that would be beaker C, because it had exactly 3.6. All right, 3.6 in there exactly is beaker C from above. All right, our extension questions for today. Let's look at number 18. It says predict what would happen to the mass of solid solute sitting at the bottom of the beaker in trial 8 in Model 2 when the following changes occur. Use complete sentences to support your prediction. Okay, well, if you have a beaker and you've got your solution and you've got solid crystals here at the bottom, some of them are not dissolving, and you've got others that did dissolve, they're in solution. You can't see them, but they're dissolved in solution. And then you add more water. You add more water here, now you've increased the volume of your solvent. Those water molecules that are coming in are going to help dissolve the solid particles down there. If you add more water, then more solid will dissolve. And you will see Remember we had 3.6 grams here that were dissolved and the 4.4 that did not dissolve. You're going to see some of these being dissolved, and this number 3.6 is going to increase, the 4.4 is going to decrease. If the beaker is heated, if the temperature goes up, the solubility, in general, there are exceptions where it doesn't, the solubility usually increases for the solvent. Water, definitely, because these particles now, these water particles, have a lot more energy, and they can come in here and break these crystals apart and contain and hold on to more because of the increased energy that they have. So when you increase the temperature, particles are going to gain more kinetic energy, and they're going to be able to dissolve more particles when they have more energy. Alright, the beaker is allowed to sit uncovered for 2 days and some water evaporates. Well, if you take water out, now you're going to reduce the amount that can be dissolved in there. Less water can't hold as much in the solubility state. They won't be able to dissolve as much. So that means the reverse is going to happen here. This 3.6 is going to go down. Some of these crystals that are dissolved in the water are actually going to be formed, are going to be visible. They're going to turn into visible solid crystals. And the 3.6 is going to go down, the 4.4 is going to go up because the water is being taken out. So less will dissolve. Okay? Those are great little kind of questions for you to kind of see if you really understand what is happening here with solubility. All right? I'm going to mention one last thing before I sign off, and that is when you have reached solubility. So we have a solution here, and we've got dissolved particles in our solution, and we notice, oh, there's a bunch of solid down here at the bottom of our container, and therefore it doesn't matter how hard we stir this or how long we stir this, if we're not going to change the temperature, those solid particles down there are never going to go away. Then we know that this is saturated. Okay, we already mentioned that. But I just want to mention something really quickly here. What really is happening in a saturated solution is that this is in a state of equilibrium. What does that mean? Equilibrium means that there is a lot of activity still happening here. It doesn't mean that things have stopped. It doesn't mean that the process of dissolving and recrystallization has stopped. All it means is that any time that you have crystals that are going to dissolve, you are going to have the same number of crystals recrystallize, or same number of particles, okay? There is a constant flow from one to the other. But once you have reached saturation, this direction, the two directions are going to be equal in their rate. So the dissolving process is equal to the recrystallization process, and you're not going to see any change in the quantity of solid crystals at the bottom of the container. Okay? But that doesn't mean that things have stopped. You constantly have the dissolving and recrystallizing process happening. It's just that once you've reached saturation, the direction of those two, the rates of those two have become equal. And until that point, until you reach saturation, the dissolving process is really all that's happening, or at least happening to a greater extent, and you don't see the recrystallization. But once you've reached saturation, now these two processes are going to be equal in their amount that is happening, the rate that is happening, and you're not going to see any change in the amount of solid that's at the bottom of the container. Okay? So saturation means the two processes are happening at the same rate, and that state is called equilibrium. You might see that in the future. All right. I will see you in the next video.